In this video, I'm going to talk you through standardized scores, covering what they are, how they are calculated, and how to interpret them. The advantage of standardized scores is that they allow you to compare a particular student's score with the scores of other students in the same year group, of the same age, or who you would expect to be at a similar level. So what do they mean, and how do we derive them? Let's look at some raw scores from an assessment. Here we have a list of scores alongside corresponding frequency, that is, the number of students who got a particular score. There are 10,000 students in this cohort. What happens if we plot these data? What we see here is a distinctive bell-shaped curve. This is great because this sort of curve is well behaved and well understood statistically. Here we see our sample of 10,000. With sufficiently large samples, say of a few thousand, the frequency distribution tends to be evenly distributed and well behaved, like this one. We can also plot it like this. If we calculate the mean or expected value for these data, we get 27.0515. If we calculate a measure of how spread out the data is, what we call the standard deviation, we get 6.9323. I'll talk a bit more about the standard deviation later. This maps onto a well understood statistical function called the normal distribution. That's this nice smooth function in red. This is a very common, well-behaved function, and because of that we can confidently use standard statistical manipulation to shift this function. Instead of a mean of 27, we can make the mean anything we like. So we can make it higher or lower. Incidentally, for those of you who are statistically minded, it's interesting to note that this value in the middle, marked as the mean, is the average in every sense of the word. It's the mean, the median, and the mode of this distribution. We can also manipulate the data to have any spread we like. So we can make it a narrower spread or a wider spread. This is all done using well-established statistically valid techniques, and the fact that we can rely on these means we can say all sorts of things about our data with confidence. So let's have a look at that. Here we see our standard deviation marked on our distribution. That's our measure of spread. We know that for this distribution, 34% of our sample lies between the mean and one standard deviation away from it either side. Thus we have a central band in which 68% of the population lies. That's this yellow area. We consider anyone who falls in that band as average. Once we get outside that band, into these blue regions either side, we are significantly above or below the average, and that's significant in rigorous statistical terms. Now, if we look at these areas between 1 and 2 standard deviations from the mean, we see that 14% of the population lie in those. Finally, when we get more than 2 standard deviations away, we have the top and bottom 2% of the population. Now, let's come back to the data we were looking at earlier. It had a mean of 27 and a standard deviation of 6.93. We can standardize around any value, so let's just pick some values. One common standardization uses a mean of 100 and a standard deviation of 15. So let's see what happens when we standardize around those values. Look at how the scale at the bottom has changed. We have our mean of 100 and we have our standard deviation of 15. Here we've marked the ends of those bands at 1 and 2 standard deviations away from the mean as before. And let's remind ourselves what that means. 68% of the population is in this central band, with standardized scores between 85 and 115. These are our average scores. Outside of that, we're significantly above average if we're over 115, and significantly below average if we're below 85. So let's look at a chart of standardized scores. We can see at a glance who is above and below average, and have an understanding of whether or not that is significant. If we look at Ian, Gillian, Casper, Barbara and Anne, we can see that they have scores that lie between 85 and 115, thus we would consider them all to be average. However, it is also worth noting that a difference between any two scores of more than 15 we would consider significant. So for example, Ian has a score of 89 and Casper has a score of 110. Well, that's a difference of 21, that's more than 15, that's a significant difference in standardised score. Now let's look at Frank. Frank has a standardised score of 82. That's in that band below the average, is significantly below average. Similarly, if we look at Diana, she has a score of 121, that's above 115, so that's significantly above average. Now if we look at Harry, he's got a score of 65, that's in that bottom 2%. And Eloise has a score of 132, well that's over 130, that's more than 2 standard deviations away from the mean, she's in the top 2%. So, in summary, standardised scores provide a measure which always behaves the same way statistically. They allow you to compare the scores of a particular student, or even a whole cohort, with the scores of other students in the same year group, or with students who did an assessment in another year. You can tell at a glance whether any differences are significant and know that it is backed up by rigorous statistics. And here we see a brief summary of what those different bands mean.